recall the system of equations that we obtained for mixing in two tanks. There's nothing in this situation that says we can't vary the rates R1 and R2, although in the simplest cases, in the cases in which we can most often find solutions, we will have constant rates. But these rates could be variable, so that the equations that we get down here, I say the rates could be variable as long as they obey the constraints of conservation of volume and so forth. The equations that we get, then Q1 prime could be some function times Q1 plus another function times Q2. Q2 prime, some function times Q1 plus another function times Q2. And we could have even another function on here that isn't dependent on Q1 or Q2. In general, then, we could consider equations, let's get my, of the form Q1 prime equals, let's use A11 for the coefficient of Q1 and A12 for the coefficient of Q2, understanding that A11 and A12 might be constant, they might be functions of t, and then plus B1, which also might be a constant or might be a non-constant function of time. Q2 prime could then be written in this form. And of course I've written the coefficients in such a way that it's natural to translate this equation into a matrix equation. So the matrix equation is just what we get if we let the left-hand side be Q1, Q2 quantity prime, which is going to give us Q1 prime for the first row, Q2 prime for the second row. And the matrix is going to be just A11, A12, A21, A22, which will be multiplied by the column vector Q1, Q2, so that if we multiply this out, our first row will have A11, Q1, which we want in the first row, A12, Q2. And the first row of this last vector, B1, B2, is going to be B1, and our first row then matches the first equation. The second row of this matrix product will match the second equation. Now, as an afterthought, I put t's in parentheses after each one of these A11, A12, A21, A22 functions and the B1 and B2 functions. They don't look very good, but that's what's going on with that thing that you probably can't read. So that our equation can be written as follows. This column vector, the column vector Q1, Q2, I'm going to call that just, column vector Q. I'm going to put an arrow over it, and now it stands for the column vector Q1, Q2. This matrix I'm going to call A of t, fairly natural thing to call a matrix whose coefficients are A11 through A22, and then that's multiplied by the Q of t vector. And then I'm going to write this column vector as the B of t vector, so that now the system of equations is written as a vector equation in which the Q of t vector is multiplied by a matrix. Now this is just a notational convenience, but as we're going to see, we can pull a lot of machinery out of matrix algebra to make the solution of this sort of system a lot simpler. Now we're going to use a more general notational convention for the general situation here. Okay, the equations are going to be like y1 prime equals a11 y1 plus up through a1n y sub n plus, we could call it b sub 1, and down through y sub n prime equals a n1 y1 plus up through a n n y sub n plus b sub n, where we have all the equations for y2, y3, etc., following the same pattern of subscripts. So that this equation is going to be, well, first of all, if I let y equal the vector y1 through y sub n, and I'm going to use p of t for the coefficient vector. So p of t will be the matrix a11 through a1n, an1 through ann. In other words, the aij matrix. And I'm going to use g of t for the matrix b1 through b sub n. Then the system becomes y prime equals p prime of t, it's p of t times y plus g of t, and let me get rid of that prime. Now I'm going to complete the transformation of the variables here. I'm going to call this, instead of a11, p11 up through p1n. So instead of a's, I'm going to call these coefficients p. So I'm just going to go through and change all those a's to p's. A little sloppy, but could be worse. And these b's could be g's, but I'll just leave them as b's. You can imagine they're rotated 180 degrees and curled a little bit on the end. You can change them to b's. Now when we talk about the p of t matrix, we won't have to talk about the components aij. They'll be pij. Just as a mixture problem could have had initial conditions, for example, Q1 of 0 equals 5 and Q2 of 0 equals negative set. Well, you can't have a negative concentration, so we'll make it plus. Okay, we could have a set of initial conditions like this that could be written then as Q of 0 equals, in this case, 5, 7. Just as we can do this, we can say that our general equation could be accompanied by an initial condition, which would be y of, let's say, 0 equals y naught. Now, this doesn't have to be 0, and you don't have to call this y naught, but some condition on the solution's y. Or more generally, let's say we have y of t0 equals y naught. So let's just kind of cross that one out and say, instead of confining this to t equals 0, let's say that our condition can be expressed at any point t sub 0. Clearly that's possible. In this one we could have said Q1 of 12 equals 5, Q2 of 12 equals 7, and we would still have had an initial condition in terms of which we could have solved the equation, or in which we could have hoped to solve the equation. That, whether we can solve it or not, depends on all these functions. So we can pose the question, does a given equation have a solution? The answer to this question is yes. If there exists an interval around t0, an interval from a to b and t0 inside that interval, and on that interval p of t and g of t are continuous, and of course that means that all the pij's and all the b1 through bn of the g function are continuous on that interval. If that's the case, a solution is guaranteed on this interval. Now, when I say a solution is guaranteed, I don't mean that I guarantee that you can find the solution, but we are guaranteed that the solution does exist, whether we can find it or not. So just to be clear about that, let's be sure we understand that the solution exists. That's what's guaranteed. There's no guarantee that we can find it. And in fact, if I just pick up random functions here, for the PIJs and the B1 through BN, it'd be very unlikely that we could actually solve the equation.